Hey everyone, and welcome back. Ready for another deep dive? Today we're going to be looking at something you see every single day but probably don't think too much about.
Oh, yeah. What's that?
Capillary action.
Ah, capillary
You
action.
know, like how water climbs up a straw or a paper towel soaks up a spill.
Right, right.
So it seems simple, but there's actually some really interesting science going on at like the microscopic level.
It really makes you wonder how much we just take for granted. Like we see liquids seemingly defining gravity.
Totally. It's like magic, but it's not.
Nope, no magic. Just the power of really tiny spaces and invisible
See,
forces.
that's what gets me so fascinated. Like, we're literally surrounded by these invisible forces that shape our world.
We are.
So, okay, what are these forces and how do they actually work?
Well, imagine liquid molecules as like tiny magnets.
Okay, tiny magnets. I can picture that.
Or to attract to each other, right? And they're also attracted to the surfaces they touch.
Gotcha.
So these attractions, we call them intermolecular forces, create a sort of tug of war
A tug of war. Between what?
between the liquid wanting to stick together, which is cohesion,
Cohesion? Okay.
and its attraction to the surface, which is adhesion.
Adhesion.
And depending on which force is stronger, the liquid behaves differently.
So that's why sometimes you see a liquid kind of curve upwards in a glass, and sometimes it curves down.
Exactly. You're talking about the meniscus.
Meniscus, right. It's like I've always noticed that curve, but I never actually thought about why it happens.
Well, if adhesion is stronger, the liquid's more attracted to the container, right? So you get a concave meniscus.
Concave, meaning it curves up.
Upwards, like water in a glass tube. It's like the water is trying to climb the walls.
Aha, that's a good way to put it.
But then if cohesion is stronger, the molecules are more attracted to each other, so you get a convex meniscus curving down.
Convex, meaning it curves down. Got it.
Like mercury. Mercury's a great example of this. It's almost like it's trying to huddle together.
So if I'm seeing a concave meniscus, I know adhesion is winning the tug of war.
You got it.
Cool. Okay, so it's this interplay of cohesion and adhesion that makes liquids behave in these, like, fascinating ways, right?
Right.
But how does this all tie back to capillary action?
Well, capillary action is essentially this interplay in action, but in really tiny spaces.
Okay, tiny spaces.
Think of like a narrow straw.
Right, narrow straw.
The liquid molecules are so attracted to the straw's surface, they actually climb upwards.
Defying gravity.
Seemingly, yes.
So the smaller the space, the stronger the capillary action.
Exactly. The narrower the space, the more surface area the liquid has to interact with.
Right, so that's why a thin straw is easier to drink from than a wide one.
You got it.
I've always wondered about that.
It's like the liquid's being pulled upwards by an invisible thread.
I love that analogy.
And speaking of pulling upwards, one of the most impressive examples of capillary action is happening all around us.
Let me guess, trees.
Tree.
I remember learning that they use capillary action to transport water up their trunks, but I never fully grasped how that works.
Well, imagine the intricate network of tiny channels inside a tree trunk.
Okay, I'm picturing it. Tiny channels.
Those channels, they act like a series of tiny straws, pulling water up from the roots, cut the leaves.
Even hundreds of feet in the air.
Even higher, sometimes.
That's wild. It's like nature's built-in plumbing system.
You could say that.
It's amazing, right? So the adhesion between the water molecules and the tree's like internal structure, it must be incredibly strong to overcome the pull of gravity.
You're absolutely right. The water molecules cling to those narrow channels, and through cohesion, they pull more water molecules along.
Creating this continuous upward flow. It's
Exactly.
mind-blowing. And this same process, it's happening on a smaller scale in our own bodies too, right?
You bet.
Like how?
Think about how capillary action helps drain tear fluid from our eyes.
Oh, wow, yeah. Without it, our vision would be so blurry all the time.
Exactly. It's incredible how this seemingly simple phenomenon plays such a crucial role.
Right, both in our bodies and in the world around us. But I'm guessing it's not all about trees and tears, right?
Definitely not.
What about, like, everyday objects?
Capillary action is everywhere. Think about every time you use a paper towel to clean up a still or a sponge to soak up water.
Wait, so the reason those things are so absorbent is because of capillary action?
You got it.
That's amazing. I never would have thought about it like that.
It's all about those tiny spaces and how they interact with liquids.
Right, right, the tiny spaces.
The porous structure of paper towels and sponges, things like that, it creates a network of miniature capillaries.
Pulling the liquid up and trapping it in their fibers.
Exactly.
So next time I'm cleaning up spilled coffee, I'll be thinking about all those tiny forces at work.
And you'll have a newfound appreciation for this invisible phenomenon we so often take for granted.
Absolutely. Okay, this is already so fascinating, and I have a question. We've talked about how the size of the space affects capillary action, But are there other things that influence how high a liquid can climb?
Absolutely.
Like, does the type of liquid matter?
It definitely does. There's actually a scientific law that explains this relationship between various factors and the height a liquid can reach through capillary action.
Oh, cool. What's it called?
It's called Jurin's law.
Jurin's law, all right.
And it's not as complicated as it sounds. We've already talked about one of the factors, the radius of the tube or the space the liquid is traveling through. But Jurin's law also tells us that the height of the liquid column is influenced by things like surface tension, the contact angle between the liquid and surface, the density of the liquid, and even gravity itself.
Wow. Okay, so there are a lot of factors at play here.
There are, but we can break them down and understand them one by one.
Sounds good to me. Let's do it.
Okay, so for instance, let's think about density. Lighter liquids will generally climb higher than denser ones. That's because denser liquids are more affected by gravity's pull.
So something like oil, which is less dense than water, would probably climb higher in a narrow tube than water would.
Exactly.
Wow, okay, I'm really starting to get this.
You're doing great.
Thanks. So this is making me think, would capillary action be even stronger on the moon, where gravity is weaker?
You're right. The weaker the gravity, the higher a liquid can rise through capillary action.
This is so cool. It's amazing how these seemingly simple concepts can have such far-reaching implications.
It really is, and this is just the tip of the iceberg. There's so much more to explore about this incredible phenomenon.
I can't wait. All right, so we've been talking about density and gravity, but what about surface tension?
Surface tension.
I remember hearing that term, but I'm a little fuzzy on what it actually means.
Basically, surface tension is the tendency of liquid molecules to stick together at the surface.
Okay,
It's like they form a kind of elastic film.
so that's what lets insects walk on water.
Exactly, and what lets a water droplet hold its shape.
Oh, that makes sense. So how does surface tension play into capillary action then?
Liquids with high surface tension are better at climbing up those narrow spaces.
So they got a stronger grip, kind of.
Yeah, you could say that. It's like they can pull themselves upwards more effectively.
And a liquid with low surface tension wouldn't be able to climb as high.
Exactly. It would be more likely to just spread out, maybe even break apart, rather than stay in a column.
I see. Wow, this is so interesting. It makes you realize how much science is going on, even in the simplest things.
Right. It's everywhere.
And the more we understand these, like, fundamental forces, the more we can appreciate, the world around us.
Absolutely.
Okay, so speaking of appreciating the world around us, you mentioned earlier that Jurin's law takes into account something called the contact angle.
Oh, right. The contact angle.
What is that exactly?
Well, it basically measures how well a liquid spreads out on a surface. It's the angle where the liquid meets the solid.
Okay,
So a smaller contact angle means the liquid widths the surface better, spreading out like a thin film.
so like water on a clean glass surface.
Perfect example. That's a small contact angle.
Gotcha. So if a liquid has a small contact angle, it'll be better at climbing during capillary action.
You got it. It's like it has a stronger attraction to the surface, so it can pull itself up easier.
What about the opposite, like liquids that bead up on a surface?
Ah, you mean like when water hits a waxed car?
Yeah, exactly. It just beads up and rolls right off.
That's a great example of a large contact angle.
Okay.
In that case, the liquid molecules are more attracted to each other than to the surface, so they clump together.
Instead of spreading out.
Right.
So the contact angle plays a big role in how well a liquid can climb.
Big role, yeah, along with all those other factors we talked about.
Right. Density, gravity, all of that.
It's all connected.
It really makes you think about how much is going on with like a simple water droplet.
It's more than meets the eye, for sure.
So far we've talked about capillary action in nature and in everyday objects. Are there any other areas where this phenomenon is like being used?
Oh, definitely. And some of them might surprise you.
Oh, like what?
For instance, did you know capillary action is actually crucial in how diapers are designed?
Diapers? Really?
Yeah, they contain materials called superabsorbent polymers.
Superabsorbent polymers, okay.
They can soak up incredible amounts of liquid.
How?
These polymers create a network of tiny spaces, like miniature capillaries, that pull moisture away from the baby's skin.
So it's like a built-in system of tiny straws.
Exactly. It's an ingenious way to keep the baby dry.
Wow, that's pretty cool. And what about other applications?
Well, capillary action is also playing a key role in a cutting-edge field.
Okay, tell me more.
It's called microfluidics.
Microfluidics sounds high-tech.
It is. Basically, it's the science of manipulating tiny amounts of liquids, often on a really, really small scale.
Okay.
Think microscopic.
Wow. And what's it used for?
Lots of things. Medical diagnostics, environmental monitoring, all sorts of things.
Cool. So where does capillary action come in?
It's used in these microfluidic devices to control how liquids flow.
I see.
Imagine tiny channels etched onto a chip with capillary forces moving the fluids.
So we're talking about controlling liquids at a level you can't even see?
Pretty much. And that level of precision opens up a whole world of possibilities.
Like what?
Well, microfluidic devices can be used for rapid blood tests,
Really?
analyzing DNA, even creating miniature organs for testing new drugs.
Wow, that's incredible. So something we see every day is actually at the forefront of cutting-edge technology.
It really is. It just goes to show how important it is to understand these basic scientific principles.
Right. So something as simple as capillary action, it can have a huge impact on our lives.
Huge impact, yeah.
I'm starting to see that. This whole conversation is making me look at things differently.
That's what we like to hear.
Okay, so you mentioned that microfluidics is being used in environmental monitoring.
Oh, right.
Can you tell me a bit more about that?
Sure. So they're developing these portable sensors.
Portable sensors.
Yeah, and they're low cost too. They can detect pollutants in water or air,
Okay.
and they use capillary flow to move tiny samples through microchannels where they can be analyzed.
So it's like a mini lab on a chip.
Exactly.
And it's all thanks to capillary action.
All thanks to capillary action.
Wow, that's amazing. This technology could really change things.
I think so. It has the potential to make environmental monitoring much more accessible.
This is incredible. I never would have imagined that capillary action could be used in so many different ways.
It's amazing what you can do when you understand the science behind it.
This has been a really eye-opening deep dive so far.
I'm glad you're enjoying it.
Oh, I am. But I'm sure we've only scratched the surface of all there is to know about capillary action.
You're absolutely right. There's always more to learn. That's what keeps science exciting.
I can't wait to see what other surprises capillary action has in store. Okay, so we've seen how capillary action is being used in all these high-tech fields like microfluidics.
Right.
But are there any ways it's being used for, like, more sustainable solutions?
Actually, yeah, there are quite a few. For example, researchers are exploring how to use capillary action to create self-watering planters.
Self-watering planters. That sounds pretty cool.
It is. They help conserve water, too.
Okay, how do they work?
Well, these planters have a reservoir of water at the bottom,
Okay, a reservoir at the bottom.
and a material with good capillary action acts as a wick, pulling water up to the plant's roots.
So the plant is always getting water without having to water it all the time.
Exactly. It's a pretty smart way to make sure the plant gets a steady supply of water.
That's really neat. It's like those science fair projects, where you use a string to draw water from one cup to another.
Haha, yeah, kinda, but obviously on a much more sophisticated level.
Right, of course. So it's taking a simple principle and, like, applying it in a way that helps the plant and the environment.
Exactly.
It's amazing how versatile capillary action is. It's like this hidden superpower that we're just starting to figure out.
I like that, a hidden superpower.
Speaking of superpowers, some researchers are even looking into using capillary action to generate energy.
Oh yeah, that's a really interesting area of research.
Wait, really? Generate energy? How is that even possible?
It's still pretty early stages, but the idea is to harness the movement of liquids through those capillary channels
Okay.
and use that to create a small electrical current.
That sounds like something out of a science fiction movie.
I know, right? But it just shows how creative scientists can be, finding solutions inspired by nature.
It's incredible to think that something you usually don't even notice, like capillary action, could be part of a more sustainable future.
It really is. It's a good reminder that even the smallest things can have a big impact.
This whole deep dive into capillary action has been amazing. It's really made me realize how much science is happening all around us.
I'm glad you enjoyed it. It's always fun to explore these topics and see the connections.
Yeah, it's like you start to see the world differently.
Exactly.
Well, I think our listeners are going to come away from this with a whole new appreciation for capillary action.
I hope so. It's a fascinating phenomenon, and it plays such a big role in our lives.
It really does. So, to wrap things up, I want to leave everyone with a final thought. Keep your eyes open and your minds curious. You never know what incredible discoveries are waiting out there, even in the most unexpected places.